Alright guys, I hope you're ready for another episode of Tips and Tricks. If you like the video, please remember to like, comment, and subscribe in the comments below. Alright, so this time we're going to do 5 and 6, and when you look at number 5, it's kind of a unique situation. Typically we've been dealing with stuff that's been floating in this unit, but in this case the rock sinks. Alright, they gave me the mass, they gave me the volume of the rock, and it sinks to the bottom of a freshwater pond. I want to know if the rock is resting on what I'm assuming is flat bottom of the pond, how much force is exerted by the normal force of the pond pushing on the rock. And this seems kind of like a rough problem, right? Unique situation. How do we solve this? Well, let's start by doing a force diagram. I find a lot of these buoyancy problems get a lot easier if you consider the force body diagram going with it. How many forces are acting on this rock right now, right? Force number 1, obviously the rock weighs something, right? So it's got a weight. Okay, and that's pointing down. There's a normal force. The bed of the pond is pushing up on the rock. So that's a normal force. Okay. Now, believe it or not, the rock is in fact submerged in water, so there is a buoyant force pushing up on it. Okay. So when we set up this problem, you're looking at the weight of the rock is equal to the buoyant force of the displaced liquid plus the normal force on the rock. Sorry, I almost wrote Fn. Okay. And we're trying to solve for the normal force acting on the rock, right? So that must mean that we can fill in these two things. Weight of the rock is pretty simple. I mean, you know, you're doing mg for that one. That shouldn't be too hard. The tricky part is the buoyant force part, right? Remember the buoyant force breaks down into the density of the liquid displaced, okay, the volume of the liquid displaced, times little g, because we happen to be on Earth. This is an earthly pond. We haven't gone to like Uranus or Neptune or something like that and dropped a rock in that pond, all right? Okay, so rho is really the only tricky thing in here. Remember that you're in fresh water. The physics lawyers were incredibly specific when they talked about that. We were in a freshwater pond. Sorry about the unfocus there, right? So in a freshwater pond, the density of the water is going to be 1,000 kilogram meters cubed, okay? Obviously, the volume is going to be the volume of the rock because that is the amount of liquid displaced, and you go from there, okay? For number 6, we're going to do something similar, right? It's talking about a styrofoam raft, not great for ecology, all right? Styrofoam takes a while to break down in the environment. They shouldn't be making their rafts out of styrofoam, but whatever. It was probably the 90s, right? Has a density of 100 kilogram meters cubed and measures at 2 meters by 1.5 meters by 20 centimeters. I'll give you 3 guesses as to what you're supposed to do with that 20 centimeters, okay? And since this is a video and you can't interact with it, I'm going to assume you know to change it into meters. If we do our force body diagram, okay, all right, they give a very important stipulation. What load will cause the raft to be submerged exactly halfway into the water? All right. So when we set up our force body diagram, we know that the raft weighs something. We know that there's a buoyant force from the water pushing up on the raft. And we also know there must be some additional weight of something on top pushing down. All right, so we got 3 forces. Okay, I've got 2 arrows going down. They're working together. And I've got 1 arrow going up. That's the buoyant force, so that must be on its own. Okay. So now, we're solving for this weight of the load, right? So we must be able to fill in for the weight of the raft and for the buoyancy. Now, the weight of the raft is actually pretty easy to do. So remember that in the past we've said weight's equal to mass times acceleration due to gravity. But in this unit, if you consider that density is equal to mass divided by volume, you could say that mass is actually equal to density times volume. So anywhere we see that mass, we're going to plug in density by volume. Okay. All right, so just notice normally the weight of the raft would be m times g. Instead, I'm taking the mass and I'm plugging in rho v where the mass normally goes. On the other side, I'm doing the exact same thing, but this time for water. Okay. Now here's where things get tricky. The raft side is actually pretty cut and dry, right? The raft's volume doesn't change, nor does its density, nor does 9.8 meters per second squared. But what volume are we going to plug in for the displaced water here? Well, remember what the physics lawyer said before. We want it to be submerged exactly halfway into the water. Well, when you calculate this volume here for the water displaced, don't forget to consider that perhaps you're not going to be using the entire thickness that you had to convert into meters, right? In fact, if you want it to be halfway, you probably have to use half the thickness. Okay? Anyway, those are my tips and tricks for 5 and 6. Good luck on those. I'll be posting solutions to these problems tomorrow with me sort of going through maybe a little bit. I haven't decided if I'm going to do just the work or if I'm going to do a little video on exactly how to go through everything. I'm also going to put up a little poll, guys, to see how helpful these videos have been, whether or not you want me to keep them going or you want me to do, something else. All right. So I hope you guys enjoyed 1 through 6 on buoyancy. Happy buoyanting.